Okay, so what we're going to look at is how do we do similar calculations for the different points in this pH titration curve here for a weak acid, strong base titration. So the example we're going to use is acetic acid reacting with sodium hydroxide to form sodium acetate and water, all right? So what we're going to do is a series of questions where we're looking at different points along the titration curve so that we can basically calculate the pH based on the amount of the base added. All right. So I'm going to get out of this here and go to the question themselves. And this basically is the same questions on which the previous slides were based on. The only difference is that we replace hydrochloric acid with acetic acid. All right. So what you're going to see is that because acetic acid is a weak acid, it is not as easy to calculate the pH at the different points, including at the initial point. All right. Which is what we're going to do in A. Right. So therefore, we can't assume a complete dissociation of the acid because it's weak. We have to take into account that the dissociation is partial, and that is what you're going to see in each step of the calculations that we'll be doing here. So we're going to start off with the A part, which is saying what is the pH before any sodium hydroxide is added. So basically what we're doing is finding the pH of the acetic acid before we add any base. So let me go to let me open up a new, okay, so let me do that. Okay, so first thing I'm going to do is, because it's a weak acid, I'm going to write down the equation for the dissociation of the weak acid. So it is HA dissociating to form H plus and A minus. All right. So the initial concentration of the acid, and by the way, HA would be the weak acid. In this case, it's acetic acid. For these problems, you don't need to write down the full formula for the acetic acid or whatever the acid is. You can just use the generic HA to represent your weak acid, all right? Which is what I'm doing here. And that's basically for the purpose of brevity, saving time and all of that. So the initial concentration of the weak acid is 0.100. This would be 0, this would be 0. The change is minus x plus x plus x according to the stoichiometry, so that at equilibrium, you're going to have 0.100 minus x, and this is x and x, all right? And from here, it's basically the same thing as we have done in the previous chapter, where we try to find the pH of a weak acid. We write down the expression for Ka, which is, of course, concentration of H plus times the concentration of A minus, all divided by concentration of HA, and this would be equal to x times x over 0.100 minus x, and this would be equal to x squared over 0.100 minus x, and then we assume that x is so small compared to 0.100 that this reduces to x squared over 0.100. And the Ka value is given. I forgot to point that out. Let me go back to this here. The Ka value is given here as 1.8 times 10 to the minus 5. So we're going to use that Ka value right here. 1.8 times 10 to the minus 5. And basically all we have to do is solve for x. X will be equal to the square root of 0.100 times 1.80 times 10 to the minus 5. And according to my calculations, when I did it, the answer I got is 1.34 times 10 to the minus 3. But we cannot stop there because we need to find out if our assumption that we made here is valid. And if you remember, in order for us to do that, we determine the percent dissociation to see if it's less than 5%, less than or equal to 5%. So in this case here, 1.34 times 10 to the minus 3, we divide that by 0.100 times 100%. And according to my calculations, this works out to be equal to 1.34%, which is less than 5%. So therefore, assumption is valid, right? So therefore, we can go ahead and use this value to represent the concentration of H plus times 10 to the minus 3 m, which means that the pH is equal to minus log of 1.34 times 10 to the minus 3. And according to my calculations, this works out to be equal to 2.87. All right, so that's the pH of the solution at the beginning before you add any sodium hydroxide. And just to point out to you the correspondence in the graph itself, you'll see that right here is 2.87, which is the pH before you add any sodium hydroxide to it, all right? Okay, so that's basically how we calculate the pH of the initial sodium hydroxide solution before any sodium